Hello DE students, this is an overview of circuit simplification using Boolean Algebra. So Boolean Algebra is a mathematical technique that allows us to algebraically simplify a logic expression. So the simplified expressions make a circuit that requires many fewer gates. So if you start with a circuit like this and then we simplify this statement with Boolean Algebra, we can get down to this many gates and get the exact same output. So you know that George Boole lived in England in the 19th century. He worked on mathematical logic, algebra, and the binary system, and has had a unique influence on the development of computers. And that Boolean algebra is named after him, in case you did not guess. Okay, so we have a series of slides. We're going to talk about a bunch of different theorems. The last slide in the PowerPoint has all of the theorems. I'm going to go in through them individually through the PowerPoint, but if you, for note-taking purposes, want to just review that last slide and copy it into your notebook, feel free to do that. Okay, so these are single variable and function theorems. So basically, theorem 1 is that x and 0 equals 0. Theorem 2 is x and 1 equals x. Theorem 3, x and x equals x. And then theorem x and not x is equivalent to 0. So basically the way this works is we can apply these theorems to different functions and it eliminates portions of our variable. So if we look down here, x and 0 equals 0, we can eliminate 2 lines of our truth table from. So we actually only have to worry about min-terms for 2 out of 4 of those. Same thing for theorem 2, 3, and 4. Okay, now looking at our single variable or functions, similar process. Theorem 5 is that x or 0 equals x, x or 1 equals 1, x or x equals x, and that x or x naught equals 1. So knowing that, we can eliminate portions of our truth table and then make our circuit significantly simpler. Okay, so taking a look at theorem number 9, which is for the inverters, that is x naught is equivalent to x. So that would mean that anytime that we have an x naught, and then going into this, we end up with x naught and x naught equals x. Now let's take a look at an example. So we can simplify this expression by applying different theorems in different sequences. Pause the video here, please, and look at the theorems and try and see if you can solve it for yourself before I go over the solution. Okay, if you are hearing my voice now, that means you paused the video, you attempted to solve this using the theorems that you've already seen, and now that you are ready for the solution. So looking at the solution to this, we start by applying theorem 3, which allows us to simplify that circuit to A, B, or C, C naught, D. After we've used theorem 3, we can then apply theorem 4, which simplifies us down to A, B, or 0D. Going further, once we apply theorem 1, we get AB plus 0, which means that after theorem 5, we actually simplify simply to F1 equals AB. So this large expression boils down to just F1 equals AB, and that would be the circuit that we design. Now we're going to take a look at a second example. I am again going to ask that you pause the video and try and give this a whirl on your own before we move on. Okay, so again, if you are hearing my voice, that means you have paused the video, you have attempted to complete this problem on your own, and you are now ready for the solution. If that's not the case, please pause and complete. Otherwise, here is your solution. So this one we actually apply theorem 3 twice to at the beginning. So that gives us B, C naught, or B, C naught, or A naught, B 1, or A, B naught 0. After we simplified to that point, we can then apply theorem 7, which is going to give us B naught C, or A naught B1, or A B naught 0. After we have gone through there, we can then apply theorem number 2, which gives us B C naught, or A naught B, or A B naught 0. We can then further simplify by applying theorem 1, which gives us B C naught, or A naught B, or 0. And then after applying theorem 5, we're down to B C naught or AB, which gives us the final solution of F2 equals B C naught or A naught B. So now we're going to move into the cumulative law theorem. So theorem 11 is on commutative law, and it works for the and functions. So that is x and y equals y and x. And for or functions, that would be x or y equals y or x. We also have theorems for the associative law, which means that x, y, z equals x, y, z. And for the and function, we have x or y or z equals x or y or z. Distributive law, same thing with the and function, x, y, or z equals x, y, or x, z. So we can distribute that x throughout. And same thing with the or function. If we have x or y and w or z, we can then get xw or xz or yw or yz. So now take a moment to try and solve this problem using those new theorems that we just added, as well as those older ones that we took in before the first couple of examples. Take a moment and pause this video, and then we'll talk about the solution. Okay, so if you are hearing my voice, that means that you have paused the video and you have attempted to solve this problem on your own. So let's take a look at the solution. So we start out by applying theorem 15, which is resulting in R naught T or R naught, or RT, or S naught R naught, or S naught T. We can then apply theorem 4. Theorem 4 then simplifies us to R naught T plus 0 or RT, or S naught R naught, or S naught T. After we apply theorem 5, we then end up with R naught T or RT, or S naught R naught, or S naught T. Theorem 14 can then be applied after that, which simplifies us to T, R naught, or R, or S naught, or S naught R naught. We can then go one step further and go to theorem 8. Theorem 8 is going to give us T, 1 or S naught, or S naught R naught. We can then apply theorem 6, which gives us T1 or S naught R naught, and then our final solution using theorem number 9 is going to give us T plus T or S naught R naught. Okay, so then moving into consensus theorems, so 16, 17, 18, 19 focus on consensus. So theorem 16 is x or x naught y equals xy. And 17 is x naught or xy equals x naught y. And then theorem 18 is x or xy equals xy naught. And then theorem 19 is x naught or xy naught equals x naught y naught. So basically these theorems are coming to a consensus, as they describe, to give us the simplified solution. All right, so go ahead and try and solve this guy. I have a feeling you're definitely going to see consensus theorem here, but go ahead and pause the video, and then we will move on from there. All right, so if you are hearing my voice, that means you pause the video and you have your own solution to compare to this solution right here. So we start out by using theorem 14. Theorem 14 allows us to simplify to P and S or Q naught S naught or PQS. So then by applying theorem 18, we then have P and S or Q naught or PQS. We can then go further using theorem 14 twice, which is going to result in PS1 and 1 or Q or PQ naught. Moving to theorem 6, we then get PS1 or PQ naught, which then results in us using theorem 2 to get our final solution of PS or PQ naught. All right, and then this is that summary slide that I told you about at the beginning. So then over here you have your theorems 1 through 9. Then we have 10 through 19. These are identified with their different laws that they follow versus the introductory theorems, which are 1 through 9. Feel free to get this into your notes or print this slide and tape it into your notes. Either way, you're going to want this for a reference as you move through the Boolean Theorems activity that is posted in Classroom.